Now the question is why? Well, our data doesn't give us enough information to be able to tell you the full story as to why yet, but here are a few possibilities. The main one is probably acoustic waves. So the Great Red Spot is a giant hurricane, a giant storm. As you're probably aware from similar storms at Earth, they generate lots of high degree of winds and turbulence. And also just general disruption of the atmosphere that would lead to wave propagation and generation. So if the same thing happens at Earth, that is, an Earth hurricane might generate waves, then we might expect the largest hurricane in the solar system, i.e. the Great Red Spot, to generate even stronger waves and a much wider degree of wave activity. So Schubert et al. 2002 looked into the possibility of acoustic waves and what they would do to Jupiter's upper atmosphere. And Schubert et al. Found that basically acoustic waves would be generated in the lower atmosphere of Jupiter, could potentially deposit energy into the upper atmosphere of Jupiter. I say potentially because Schubert et al. Didn't have any good observational constraints to tie their model estimates to. And so they had to evaluate a wider range of possible waves that may actually be present in Jupiter's atmosphere. And Schubert et al. Also noticed that gravity waves, so there's another family of waves that people think may provide a transport of energy from the lower atmosphere to the upper atmosphere, called gravity waves. They found that gravity waves may actually cool the upper atmosphere rather than heat, or at least there's some uncertainty about whether they would provide heating or cooling. Okay? So, if the Great Red Spot is generating acoustic waves, then it is possible those acoustic waves would transport energy from the Great Red Spot vertically upward to where that energy would be deposited in the upper atmosphere and therefore heat the upper atmosphere. And so this is one consistent explanation for the Great Red Spot hotspot that we've seen in the H3 plus temperature. And in fact, we've seen other similar processes at Earth. So it's not so strange to imagine that acoustic waves could heat the upper atmosphere. We see dissipating acoustic waves that locally heat the Earth's atmosphere by tens of Kelvin per day, and other wave structures that lead to heating of the Earth's upper atmosphere, such as mountaintops, volcanoes, just other sources of acoustic waves and other wave activity that have been observed to work in that they transport energy from the lower atmosphere of Earth to the upper atmosphere of Earth. So, at this point, the explanation of the Great Red hotspot is a hypothesis. It's probably acoustic waves. That hypothesis is yet to be tested. More work is needed. In particular, we need to know observationally what are the properties of waves that are possible in Jupiter's lower atmosphere, and therefore, what is the rate of energy transport that is possible from the lower to upper atmosphere. So, while the explanation is just a hypothesis, the observation stands, and that is the upper atmosphere above the Great Red Spot is the hottest point anywhere on the planet at Jupiter. And so that requires some explanation. When we did this work, we worked with some artists to generate a concept of how this might be happening. And so here's a nice figure that Karen Taramura put together, who is an artist that works with the University of Hawaii and is associated with the IRTF where we did these observations. And so she illustrates the Great Red Spot, and then the upper atmosphere where we measured the temperatures in H3+, which is significantly above the Great Red Spot. So something like 700 kilometers altitude above the Great Red Spot, where we find a hot spot. And you see these arrows and these sort of wave structures sort of representing a possible transfer of energy from the lower atmosphere to the upper atmosphere via waves. So these acoustic waves that might be breaking and heating the upper atmosphere. We put out this figure and another nice figure, as well as just a news report. And surprisingly, this article was picked up by more than 147 news outlets. So it left us in a sort of Twilight Zone experience where people actually cared about the science we were doing. This doesn't usually happen for scientists, so it was very strange. We had TV interviews, radio interviews, all newspaper interviews. The story was on the front page of the BBC Science page, on the front page of NASA, so it's just very confusing to deal with the attention. I think it all comes down to the fact that Jupiter is kind of cool, being the biggest planet in the solar system. The Great Red Spot is kind of cool. It's a very ominous looking structure on Jupiter. And thinking about the hottest and the heat that's happening above the Great Red Spot is also kind of cool. Who knows? As part of this media frenzy, there are a lot of media outlets that put their own videos together. And this one in particular, we found did a very good job of sort of explaining the idea of what's happening in a relatively straightforward and brief amount of time.
Jupiter's iconic spot is turning up the heat. Mankind is beginning to unravel the mysteries of our solar system's biggest planet, starting with its atmosphere. Jupiter's atmosphere has roughly the same temperature as that of Earth, despite being 5 times farther away from the Sun. Dubbed the planet's energy crisis, this detail has long puzzled scientists until now. The explanation for the gas giant's superheated atmosphere lies in its Great Red Spot, which is a massive 10,000-mile-wide hurricane with 400-mile-per-hour winds that has been raging for centuries. Jupiter's atmospheric temperatures are around 1,700 degrees Fahrenheit, but the area directly above the Great Red Spot is hundreds of degrees hotter. This suggests a link between the planet's upper and lower atmospheres, despite being separated by a vertical distance of 500 miles. The heat is likely caused by high-energy acoustic waves shooting up from the storm. The waves cause atoms in the air to move around, raising the temperature. NASA expects to gather more information from the Juno spacecraft, which is now in orbit around Jupiter. Now that scientists have discovered why the atmosphere is so hot, maybe they can also figure out why the spot is red.
Okay, so just to summarize Jupiter's Great Red Spot, hot spot, we found that Jupiter's upper atmosphere, despite being about as 5 times from the Sun as the Earth, is just as hot as the Earth's upper atmosphere. And so that implies there's additional sources of heat that are responsible for those observed temperatures. At present, we don't know what those sources of heat are, and so we have what we call a giant planet energy crisis. In other words, where is that heat coming from? These ground-based observations of H3+ find that the upper atmospheric temperature above Jupiter's Great Red Spot is significantly higher than anywhere else on the planet. So there's a GRS hotspot. So it's circumstantial evidence for a transfer of energy from the lower atmosphere to the upper atmosphere. If it happens above the Great Red Spot, it might also happen elsewhere. And it might be that the Great Red Spot, hotspot, is just sort of a smoking gun signature of this process. Why we might think that? Well, because the Great Red Spot is the largest storm in the solar system. So if storm activity is responsible in part for heating the upper atmosphere, then it would be easiest to measure above the largest storm in the solar system. But it might happen to a smaller degree around other storms at Jupiter, which there are many, and around other storms at other giant planets, of which there are many. So it may just be that this is the first observation that gives us the clue to look for further heating above other storms throughout the solar system. Finally, how we need to follow up on this work is in a few different ways. One, we need to continue to follow up with ground-based observations. These have been very preliminary in the sense that we could do much better from the ground. That just takes more time on telescopes and more dedicated observational programs. So we can do that using big telescopes in Hawaii, such as Keck and IRTF, and in Chile, such as the Very Large Telescope, VLT. In addition, what we need to do is to understand the altitude profile of the temperature in Jupiter's upper atmosphere. So all of these observations that I've described so far are integrating the emission from H3+ through a column of gas. And so it convolves the information about how temperature varies with altitude and how density varies with altitude. And the signature of a transport of heat from lower atmosphere to upper atmosphere would change the way the altitude profile of temperature looks. So what we really need to do is figure out what that profile is. Now there's also a potential for follow-up of this research by the Juno spacecraft, which is now orbiting Jupiter. So Juno has high elliptical orbits that come in over Jupiter's poles and get very close to the planet near Jupiter's equator. And so they have some instrumentation that can follow up and look for further clues as to what's happening at the Great Red Spot and above the Great Red Spot. And finally, let's just summarize all together these two different observational results at Jupiter and Saturn and what those implications are for giant planets in general. So one point that I didn't emphasize strongly enough yet is that the upper atmosphere is a key transition region or boundary layer between the dense atmosphere below and the tenuous energetic space environment above. So if you think about it, the atmosphere that we're used to, the atmosphere that we're breathing, the so-called dense atmosphere near the surface of the Earth, at some point you have to transition from that atmosphere to the vacuum of space, where there's almost no atmosphere, right? And much of the important transition from that dense atmosphere to space happens in the upper atmosphere. As with many other areas of physics, boundary regions are always interesting regions to study because interesting physics happens there. And so energy can come in from above, such as from photon or energetic particle deposition, and that's all absorbed in the upper atmosphere. And energy can come from below, such as waves. And so this is a very dynamic region where a lot of interesting physics is happening. And it ties together other different regions that sort of comprehensive knowledge is required to really understand atmospheric physics in general, or even space physics and its interaction with planetary atmospheric environments. So the upper atmosphere is a tremendously useful region of atmospheric research to focus on. And finally, it also is where atmospheric escape tends to occur. So if we're interested in looking at planetary habitability and the evolution of atmospheres and generation of atmospheres, this is another area of research that is well represented by upper atmospheric study. The giant planet upper atmospheres are particularly unique in the sense that we can actually monitor them easily from the ground just by looking at emissions from the H3+ ion. So H3+ ion has lots of infrared emissions, and some of them can be observed in an atmospheric window from ground-based telescopes. So it's unique that we can actually monitor densities, temperatures, and the energetics of the upper atmospheres of the giant planets relatively cheaply from the ground at Earth. We can do that year-round, and we can continue to derive global properties of the upper atmosphere of the giant planets. We can't do the same thing at Mars or Venus, and we wouldn't be able to do the same thing at Earth even if we were looking back at Earth from, say, Mars. So the giant planets are very unique in that respect. This offers a low-cost alternative for spacecraft missions. Obviously, it's tremendously useful to have spacecraft directly at the planets because you can do a lot of things that you could never imagine doing from the ground. But at the same time, they're expensive and rare, and they can't be everywhere at once. And so ground-based observing is a great way to support spacecraft measurements and also to supplement them when they're not available. So for example, before Juno was at Jupiter, we could do ground-based observations. Now that Juno is there, we can work in concert with Juno. And when Juno's mission ends, we can continue to monitor the upper atmospheres of Jupiter, and we can put together a long-term picture of Jupiter's upper atmosphere. It just wouldn't be possible otherwise. Finally, we study Jupiter and Saturn because they're interesting objects in their own right, but also because they have relevance for understanding other planetary atmospheres, such as the Earth, and understanding other planetary atmospheres, such as exoplanets. So this field is called comparative planetary studies, and it's very fruitful to compare and contrast different planetary atmospheres in that they give you insights, the differences and the similarities give you a lot of insights into the physics that's dominating what you're observing at these different planetary atmospheres.